The completeness axiom or property of real numbers implies the following fundamental results of real numbers: the Archimedean property, existence of roots of polynomial equations, density of rational and irrational numbers in R, Bolzano-Weierstrass property for sets and sequences, convergence of sequences and series, and the Cantor Intersection Theorem. The order completeness axiom states that every non-empty subset of real numbers that is bounded above must have a supremum or a least upper bound in R. This foundational property acts as the mathematical glue that fills all the infinitesimal gaps present in the rational number system, ensuring that the real number line is a continuous, unbroken continuum. Without this axiom, calculus and mathematical analysis would entirely collapse. It serves as the logical bedrock for several critical theorems such as Archimedean property, density of rational in R, Bolzano-Weierstrass theorem, Cantor Intersection Theorem, convergence of sequences and Cauchy sequences, convergence of series, the intermediate value theorem. It defines R as a connected space, a topological notion. Without completeness, the real line would be totally disconnected and shattered by missing irrational points. It forms the basis of Banach spaces and Hilbert spaces, which are essential frameworks for solving differential equations and modeling quantum mechanics. There are three equivalent statements of Archimedean property. The first one says that for every real number x, there exists a natural number n such that n is greater than x. The second one says that the set of natural numbers is not bounded above in R. And the third one says that there is no infinitesimally small real number epsilon such that it is smaller than the reciprocals of all positive natural numbers. The property is proved using the order completeness axiom of real numbers. It is a visually explained proof. The Archimedean property is a necessary condition for completeness, and completeness implies the Archimedean property. Archimedean does not imply completeness. The rational numbers are Archimedean, but they are not complete. It is used in proving the sequence 1 upon n converges to 0. It is also used in proving the set of rational numbers is dense in R. The infinitesimal form is widely used in various steps to prove many results in real analysis. No matter how unimaginably massive the universe is, and no matter how microscopically small a single atom is, one can always pile up a finite number of those atoms to eventually outweigh the entire universe. The set of rational numbers is dense in R. It actually means that between any two real numbers, there always exists a rational number. To prove it, we use the Archimedean property and the well-ordering principle of natural numbers. So, it is a consequential result of the order completeness axiom of real numbers. We can talk about the next integer or the natural numbers, but we cannot talk about the next rational number or real number. The term nearby or topological notion of neighborhood starts to develop. For each neighborhood or within a specific distance from a real number, we can find a rational number. If we keep decreasing the distance or shrinking the neighborhood, then the sequence of rational numbers, so constructed, gets arbitrarily close to the real number. So, it paves the foundation for defining the convergence of a sequence, the notion of limit point of a set. So it is not an exaggeration that the order completeness axiom of real numbers paves the foundation of modern real analysis. Using the density of rational numbers in R, we can show that the set of irrational numbers is dense in R too. A point X is a limit point or accumulation point of a set S if every open interval containing X contains at least one point of S distinct from X itself. In the case of a metric space, R is a metric space, it is equivalent to say that every interval containing X contains infinitely many points of S. The deep connection between limit points and the completeness axiom is perfectly captured by the Bolzano-Weierstrass theorem, which relies directly on completeness to prove the existence of limit points. Limit points serve as the conceptual catalyst for modern analysis. By shifting the focus from exact numbers to arbitrary closeness, limit points motivated the creation of the foundational vocabulary used in advanced mathematics today. The notion of a dense set can be defined in terms of limit point. The topological notion of compactness can be defined in terms of limit point. The limit point of a set, the limit of a sequence, and the limit point of a sequence are three different things, although they are closely related. The Bolzano-Weierstrass theorem for sets states that every infinite bounded subset of the real numbers has at least one accumulation point or limit point, a point where infinitely many elements of the set cluster arbitrarily closely. The theorem is foundational for understanding the topology and convergence properties of the real line. It is indispensable because it guarantees limits and extracts convergence subsequences from seemingly complicated, random, bounded processes. It is the primary tool used to prove the Heim-Borel theorem, which equates closed and bounded sets with compact sets. Compactness is what allows us to generalize properties of finite sets to continuous functions on continuous domains. It provides a reliable pathway to demonstrate the existence of extrema, maxima, or minima in optimization and calculus problems. The Bolzano-Weierstrass theorem is not an isolated fact. It is deeply intertwined with the foundational properties of the real numbers, the order completeness axiom of real numbers. We construct a new set A, consisting points X such that it is less than infinitely many elements of S. We show that A is non-empty and bounded above, so it has a unique supremum L. Lastly, we prove that L is a limit point of S. The relationship between sequences and the order completeness axiom is foundational to real analysis. A sequence of real numbers can only guarantee convergence to a real limit if the underlying space is order complete. Without this axiom, gaps exist, causing mathematically convergent behavior to fail to find a terminal value. Order completeness acts as the glue that fills the gaps in the number line. We will not deeply delve into sequences and convergent sequence in this lecture. We will do it in another lecture. What we do here is to use definition of sequence and convergence of sequence to prove Cantor Intersection Theorem directly from completeness axiom of real numbers. There are sequences of rational numbers converging to irrational numbers. It shows how important is the completeness axiom of real numbers. Cantor's intersection theorem states that the intersection of a nested sequence of non-empty, closed, and bounded subsets in R is non-empty. In general metric spaces or topological spaces, intersection of nested sequence of compact sets is non-empty. It is a foundational pillar that connects a space's structural properties, completeness and compactness, with the existence of mathematical limits. It is the primary tool used to prove the existence of fractals, such as the Cantor set, where the intersection of an infinite sequence of closed sets yields an uncountable non-empty set of points. In any general topological space, if you have a nested sequence of non-empty closed sets, their intersection is guaranteed to be non-empty if the sets are compact. This concept forms the basis of the finite intersection property of compact spaces. If the length of the interval tends to 0 as n tends to infinity, then the intersection has a unique point. The theorem is proved using order completeness axiom of real number. It shows how important is completeness axiom of real numbers. To find the nth root of a positive real number a for a positive integer n, mathematicians apply the completeness property using a set-theoretic approach. First, we define a set S which contains numbers whose nth power is less than a. We show that S is non-empty and bounded above. So by the order completeness axiom of real numbers, S has a unique supremum, x. By the law of trichotomy of real numbers, there are three possibilities. X raised to the power n is less than a, x raised to the power n is equal to a, or x raised to the power n is greater than a. The greater than or equal to and less than or equal to cases are ruled out. The only possibility is x raised to the power n is equal to a.